I'll say a few brief words about bulk modulus. That is basically how stiff the material is. So just like the tension in the string determined how fast it snapped back, the bulk modulus tells you how fast a material snaps back to its original form. Let me show you how it's defined. I'll do that analogy with Hooke's law, the spring force law. So remember, this is the spring force law, also called Hooke's law, which told you the relationship between how much you took the spring away from its happy place, right, the displacement from equilibrium, and how badly it wanted you to go back, right? And we found, of course, that the more you took the spring away from equilibrium, the more unhappy it is and the harder it pulls, right? And the proportionality constant was this thing K. We call that the spring constant, and that was basically a measurement of how stiff the spring is, right? Does that sort of ring a bell from the simple harmonic motion videos? Okay. So the same role that K plays for a spring force, bulk modulus plays for a material as a whole. So what we have is a material, and we're trying to determine the springiness of the material as a whole. So what we do is we try to compress it, and we see how much does it protest. So we cause a change in pressure, we exert a pressure, we try to smash it, and we get a sense of not how much is displaced, but how much its volume changes, right? And there is going to have to be a minus sign here, because if we increase the pressure, the volume will decrease, right? So if this is positive because we increase the pressure, this volume will be negative because we, of course, are going to decrease the volume, right? So the bulk modulus is the proportionality constant, which tells us how badly the material hates to do this. And I should tell you that for reasons of keeping this response linear for longer, we don't do straight up volume change, we do fractional volume change. So we do how much does the volume change from its initial value. And then B is that constant that goes in there. So that's how the bulk modulus is defined. It's kind of like your spring constant, but it's like a 3D spring constant. It's based on the pressure change that you are applying uniformly to the material. How much does it, or how little does it change, fractional volume change happen, and the proportionality constant is the bulk modulus. So let's go to some typical materials. Okay, let's go to compare gases versus liquids and solids. Okay. So, for a gas, the density might increase by a factor of several thousand. Let's say about 1,000. Okay. So to give you an example, we go from a gas like air that you're breathing right now to water, right? So the density of the air you're breathing right now is about 1 kilogram per meter cubed, and we know water is about 1,000, right? So if we look at this equation, we see that if the density increases, we would expect the volume, or sorry, the wave speed to go down, right? So that would seem to suggest, looking at density alone, that if we go into a liquid or solid, that the wave would move slower, okay? Because the density, the inertial stuff carried in a liquid or solid is higher, so wave would tend to go slower. Okay? Well, here's the thing. When you go from a gas to a liquid or solid, the density will go up, but we also know that liquids and solids really don't like compression, right? In fact, we've assumed that liquids and solids are entirely incompressible, right? So we've approximated that liquids and solids are not really compressible at all. We have many calculations where we said that they don't ever change shape. Well, we're going to have to relax that a little bit because if it can't carry a disturbance, it can't carry a wave, right? So we're going to have to relax that restriction and say that they're totally incompressible. But here's the thing, they really don't like to be compressed, okay? You can have a massive pressure change and barely get any volume change at all. It must mean that these bulk moduli are very large, okay? So the bulk modulus, the bulk moduli of liquids and solids, how badly they are stiff to changes is very, very high, okay? So while the density might increase, these might increase by a factor of 1,000,000 or more, okay? So yes, you trade towards a, when you go from liquids to from gases to liquids and solids, yes, you go to a more sluggish, more inertial material, but you also go to a material that will violently snap back into place when it tries to carry a disturbance. So we have two things going on here. We have that the density tries to bring the wave speed down, the bulk modulus will try to bring it up, and I'll tell you right now, bulk modulus wins. So while we have two competing factors, yes, the material gets more dense, but its unwillingness to be compressed and to snap back into position is going to far dominate. And what you will find as an upshot is that the speed of sound in solids is generally greater than that in liquids, and both of those are way, way, way bigger than the speed of sound in air or any gas. The speed of sound in liquids and solids is far, far greater. I'll tell you the result for air, for the air in this room. It is 343 meters per second. I'm just going to tell you what the answer is. You could look up what the bulk modulus is of air and put it in the density, but I'm just going to tell you the results. That's basically your value that you're going to always use. That's air at atmospheric pressure and at room temperature. So I guess I should put that as caveats. It's PATM and room temp. But you can pretty much use it and be good to go. If you have the speed of sound in solids and liquids, it's far greater. So two things I guess I'll mention about that. You see in the old cowboy movies, Native American always puts their ear to the ground to check out what's going on. That's pretty smart because you'll hear it there first. Sound travels faster through the ground than it does the air. I had an old student that told me that this had some applications in their ultrasound. So when you have ultrasound, you're sending sound. It's high frequency. You can't hear it, but it's sound. And you're sending it through various tissues. And a common misconception is that when you send it through harder tissue, that it'll slow down because it's more dense. But guess what? Hard tissue, yes, it's more dense, but it also really, really doesn't like to be compressed. And so, in fact, the ultrasound will travel faster through the hard tissue, not slower. Okay? So if you're looking at a readout and looking at the various speeds that the sound travels through different things, the more the speed is increased, the more solid that region is. Okay? So that might be a potential application for you going forward. Okay, so I think that pretty much gets out the basics. So let's start with some applications of sound. Obviously, sound plays a hugely important role in our daily lives. I guess the one thing before I put this away for the moment, this is more realistic to the type of sound wave I'm creating right now. Of course, it doesn't travel along a single axis. It travels in all directions. That's why you can all hear me, right? So in reality, it's a compression disturbance that's not moving along a straight line, like a wave on a string is moving along the string. It's going out in all dimensions. Okay? So I'm not going to get a whole lot into that, but that you should be aware that that is more realistic to the sound wave. It travels out spherically. Okay, so I think that'll cover the applets for today, but let's see what we can do in terms of perception of sound in human beings. Sound perception. There are only two things that are information carried by a wave. It's pitch and how loud it is. So pitch is frequency. They are one and the same. So if you have a low note, bass, low frequency. If you have a high note, treble, high frequency. Every musical note can be mapped directly onto a frequency. Middle A on a piano. Ding, not too high, not too low, 440 hertz. Okay? So musical notes, they all have a particular frequency. Question?
Isn't consonants and dissonance also relevant?
Those are for notes played with each other, right? We're talking about one note
But
here.
in terms of like perception, I thought.
Oh, well,
That was
this
like
is
a
this
third
is
one.
of a single wave, so I'll talk about that a little bit more. I guess I should say fundamentals of sound perception. So things that are the basic building blocks from which everything else comes from. So that's the property of one sound wave that we measured. It's its frequency. Loudness is a property called intensity. What intensity is the amount of power delivered by the sound wave per area. Okay? So for instance, I showed you that 3D picture where the sound wave is traveling out spherically, and that power is being spread over a larger and larger area. Well, that's going to make it less intense, right? So if you have a fixed amount of power, but the area is larger, then it gets quieter. That's basically because the energy is getting spread more thin. It's getting spread like butter on toast, right? If you spread it over a larger and larger area, it'll get more thin in any one spot. Okay. So this is area, and this is really only relevant for spherical sound waves because they can actually spread. So that's just kind of planting a seed for you in the future. We'll be taking a look at those sound waves that go down the tube, okay? So they don't have a chance to spread. So for instance, the area that's relevant might just be if you stick your ear on the other end of the tube, it might be the area of your eardrum that catches it, right? I guess the other thing I forgot to mention, power, of course, I haven't talked too much about it, but power is just energy per time. So intensity is just the shorthand of saying how much energy is carried by the sound wave to you per time per area. Okay? So it's the amount of energy in the wave intercepted per time per area. Okay? The units of this are watts per square meter, or if you want, joules per second per square meter. Right? A watt is joule per second. That is the property of sound that you need to know how loud is it going to be. So I'm not going to give you the entire formula because the entire formula has lots of bells and whistles in it that aren't that important for us. This is where we can start relying solely on one of the skills that I gave you starting homework 1, which is proportionalities. Okay? So the only thing that you need to know about intensity for the purposes of my class is that the intensity is related to the amplitude of the wave. So if something has a larger amplitude, it will be louder. So those are the two things that determine, I mean, that you're pretty much run out at that point of other properties that the wave could have, right? You've talked about its frequency, which is tied to the wavelength, and you've talked about its amplitude, which is in the second dimension, and that's kind of it. And I guess I'll refer to it generically as A, but of course we talked about in the sound wave, we might want to refer to it as S max or pressure amplitude, but generically it's just amplitude, okay? So you can say things like this. If you double the amplitude of the wave, by what factor is its intensity changed by? 4, right? If you triple the amplitude, it'll be 9 times the intensity, things like that, okay? So for instance, if I talk louder, then that means that the pressure variation in your eardrum is a larger variation. But if I talk quieter, it's a smaller variation in pressure, okay? So that's kind of it. And you might then wonder, that can't be all there is to a sound. Well, of course, everything else is high order things. So for instance, let me say that I played 440 hertz middle A on a flute and I played it on a clarinet. Obviously you can tell one's a flute and one's a clarinet. Even if I play those notes, exact same notes, same loudness, you can obviously say, hey, that's a flute, that's a clarinet. So why is that? Well, when you're listening to those instruments, you don't really hear just one frequency. If you made a plot of what frequencies you heard at what intensity, you do not just get a peak